The most dangerous earthquake fault in the United States is not the San Andreas. It is not the Cascadia subduction zone off the coast of Oregon. It is a fault buried under farmland in 8 states you have probably driven through without ever thinking about it, and it has its aim locked directly on the American heartland. Memphis, Tennessee, St. Louis, Missouri, Little Rock, Paducah, Cape Girardeau, Evansville. All of them sit on top of what scientists call the New Madrid Seismic Zone, and the terrifying part is not how often it moves, it is what happens when it does. According to the United States Geological Survey, a repeat of the last major sequence at this location would produce a strong shaking area 2 to 3 times larger than the 1964 Alaska earthquake and 10 times larger than the 1906 San Francisco quake. The Federal Emergency Management Agency estimates a full repeat scenario at approximately 86,000 casualties, 7.2 million people displaced, and $300 billion in direct economic losses across 8 states that were mostly not built to survive it. This is not normal news cycle noise. Something significant is buried under a huge chunk of the American Midwest, and most of the people living directly on top of it have no idea what is under their feet. Today we are going to break down exactly what the New Madrid Seismic Zone is, what actually happened during the winter of 1811 and 1812, why the same event today would be catastrophic in a way California simply cannot match, and what USGS scientists are watching for right now. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever felt an earthquake, even a small one, somewhere you never expected? Tell me where you were, what you were doing, and what it felt like. If you want to be the first to know every time something major happens on this planet, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. To understand why USGS scientists are still so concerned about the New Madrid Seismic Zone more than 2 centuries after the last major event, we have to go back to the winter of 1811, to a small settlement of about 400 people on the Mississippi River in what is now the Boot Heel of Missouri. On the night of December 16th, 1811, at approximately 2:15 in the morning, the ground under the town of New Madrid began to move in a way nobody living there had ever experienced. The first major shock is estimated by modern seismologists at a magnitude between 7.5 and 7.9. The shaking rolled the earth in visible waves. Trees snapped like twigs. Fissures opened in the ground so wide that eyewitnesses said they could not be crossed on horseback. Sulfurous gases hissed up from those cracks. And across an area of hundreds of thousands of square kilometers, people who had never heard the word earthquake sat up in bed wondering what was happening to the world. That was only the first shock. On January 23, 1812, at about 9:15 in the morning, a second major earthquake struck, estimated at magnitude 7.3 to 7.8. And then, 2 weeks later, on February 7, 1812, at 3:45 in the morning, the third and largest of the principal shocks hit, estimated at magnitude 7.5 to 8.1. That was the one that destroyed the town of New Madrid. That was the one that made history. In St. Louis, more than 200 kilometers to the north, chimneys collapsed and buildings cracked. In Nashville, walls fell. In Louisville, brick structures were damaged. And across the eastern United States, an area of roughly 5 million square kilometers, people felt the earth move under their feet. Church bells rang in Boston, more than 1,600 kilometers away. Windows rattled in Washington. D.C. sidewalks cracked in Charleston, South Carolina. It is one of the very few earthquakes in recorded history to be felt from Quebec to New Orleans, from Boston to Denver. Eyewitness accounts collected in the years that followed described birds landing on people's shoulders because they refused to fly. Wild animals were reported walking directly through frontier settlements. In the days after the December 16th shock, contemporary newspapers as far away as Philadelphia were carrying accounts from travelers who had ridden hundreds of miles east to spread the news. There was also a strange political overlap in the story. The Shawnee leader Tecumseh had been traveling the region in the fall of 1811, and later oral histories credited him with predicting the earthquake as a sign of unified resistance. That claim is disputed by historians, but the coincidence in timing is real. The earth shook while the frontier was already in political motion, and the two stories became bound together in the folk memory of the region. But the strangest phenomena of all happened along the Mississippi River itself. Flatboat operators, some of whom left detailed written accounts, reported that the river ran backwards. According to eyewitness testimony, the massive ground subsidence created by the February 7th shock, combined with an uplift on the Reelfoot fault scarp, caused a wave-like reversal of the river's flow that lasted for several hours. Water levels dropped by as much as 6 feet in places. 2 temporary waterfalls formed on what had, until that morning, been the flattest, calmest stretch of the Mississippi River. Modern geologists still debate whether the reversal was truly sustained or a series of massive back-and-forth surges, but every serious account from that night says the same thing. The river, for a period of hours, was not doing what a river is supposed to do. The land itself was permanently changed. In northwestern Tennessee, an uplift on one side of the fault and subsidence on the other created an entirely new lake, roughly 18 miles long and 5 miles wide, that we now call Reelfoot Lake. If you visit Reelfoot Lake today, you can still see the stumps of the drowned cypress forest that used to grow on that land before the ground dropped out from under it. In northeastern Arkansas, subsidence enlarged Lake St. Francis and created what are now known as the Big Lake and St. Francis Sunken Lands. In the agricultural fields of southeast Missouri, northeast Arkansas, western Tennessee, and southwest Kentucky, thousands of large, light-colored sandy patches were left across the farmland. Those are called sand blows. They are what happens when liquefied sand, forced up under enormous pressure through cracks in the ground, erupts at the surface like a geyser and then settles into a fan-shaped scar. Farmers still plow around them today. They are the physical fingerprint of the 1811 to 1812 sequence. The shaking did not stop with the third principal shock. Intermittent strong shaking continued through March 1812. Aftershocks strong enough to be felt kept happening through 1817. In total, more than 2,000 seismic events are estimated to have occurred as part of the sequence over about 5 months. The Earth's surface, according to contemporary accounts, was in a state of nearly constant motion for a large part of that winter. That changed fast. Now here is where the story stops being history and starts being a warning about right now. Because the very reason the New Madrid earthquakes were felt so far away, the very reason a fault in Missouri could ring church bells in Boston, is the reason a repeat event today would be more destructive than a comparable earthquake in California. To put that in context, we need to talk about a piece of very old geology called the Reelfoot Rift. Between 500 and 750 million years ago, during the breakup of a supercontinent known as Rodinia, the North American continent tried to split apart in a slow-motion tectonic tear that ran through what is now the central Mississippi Valley. In geology, when a continent begins to split like that, we call it a rift. Most rifts either open all the way, forming a new ocean basin, or they fail and freeze in place. The Atlantic Ocean is what happens when a rift succeeds. The Reelfoot Rift is what happens when a rift fails. The continent stopped tearing. The crack sealed itself. And for hundreds of millions of years, the Mississippi River and its ancestors buried the failed rift under kilometers of soft river sediment. But the weakness stayed. The old fault lines are still down there, and every so often, the North American plate flexes just enough to make them slip. That is what a lot of scientists mean when they use the word intraplate earthquake. Unlike California, where the Pacific and North American tectonic plates are grinding directly against each other along the San Andreas, the New Madrid Zone is not on a plate boundary at all. It is sitting inside the plate. But intraplate earthquakes come with their own set of physical rules, and one of those rules is what makes the New Madrid Zone so dangerous. To put it in simple terms, the ancient continental crust across most of the central and eastern United States is old, cold, and hard. Seismic waves travel through that kind of rock efficiently, the way sound travels through a solid steel bar. In California, the crust is younger, hotter, and more fractured, and seismic waves lose energy quickly as they move outward, the way sound gets muffled through a stack of foam. The result is that a magnitude 7 earthquake in the New Madrid Zone will shake buildings just as hard right at the epicenter as a magnitude 7 earthquake in California, but the strong shaking will extend more than 20 times further outward. Damage from a New Madrid quake does not stay local. It travels. The specific USGS finding on this is worth repeating carefully. The strong shaking area of the 1811 to 1812 sequence was 2 to 3 times larger than the 1964 Alaska earthquake, which is one of the biggest seismic events in the recorded history of North America, and it was 10 times larger than the 1906 San Francisco earthquake. When scientists talk about intraplate hazard, that comparison is what they are pointing at. And in real terms, it means the damage radius of a modern New Madrid event would draw a circle across a large fraction of the eastern United States, not just a strip along the Mississippi River. There is one more piece of the puzzle, and this one is specific to the region. Most of the central Mississippi Valley sits on top of thick layers of soft alluvial sediment deposited by the river over millions of years. When strong seismic waves pass through that kind of ground, especially when the water table is high, the sediment can behave briefly like a liquid. This is called soil liquefaction, and it is what produced the sand blows in 1811. But it is not just a historical curiosity. A modern repeat would liquefy soil under highways, under levees, under runways, under gas pipelines, and under the foundations of buildings that were never designed to sit on temporarily liquid ground. That single physical process, more than any other, is what drives the FEMA damage estimates so high. Now let us talk about the human stakes, because in 1811 the town of New Madrid had roughly 400 people. Today, the same 8-state footprint that felt the strongest shaking is home to somewhere between 11 and 15 million residents. Memphis, Tennessee, sits almost directly on top of the highest risk portion of the seismic zone. Its downtown is full of unreinforced masonry buildings that were built long before any part of Tennessee thought about seismic code. Old brick warehouses along the river, historic churches, and mid-century office buildings all fall into a category that engineers call URM, or unreinforced masonry, and URM is one of the most dangerous building types on Earth during a strong earthquake. In a scenario modeled by USGS and FEMA, a magnitude 7.7 repeat of the 1811 to 1812 sequence produces catastrophic damage in Memphis alone, with an estimated 2,500 deaths, 86,000 injuries, and $300 billion in property damage in that one metropolitan area. St. Louis, roughly 120 miles from a modeled epicenter, would still take severe shaking. Downtown Nashville, more than 300 miles away, would feel it hard. Little Rock, Paducah, Cape Girardeau, Evansville, and dozens of smaller cities across the Ohio and Mississippi River valleys would all be inside the strong shaking zone. The Gateway Arch in St. Louis was, unusually for the region, designed with earthquake resistance in mind. Most of the buildings around it were not. And then there is the infrastructure. Interstate 40 and Interstate 55 both cross directly through the New Madrid Seismic Zone, so do a series of major Mississippi River bridges, some of which carry a huge fraction of the north-south trucking that keeps the eastern half of the country supplied. So do natural gas pipelines carrying fuel from Texas and Louisiana up through the Midwest and into the Northeast. So do fiber optic backbones connecting Chicago to the south. So do the electrical transmission lines that tie together the two largest power grids on the eastern half of the continent. The 2008 FEMA Catastrophic Planning Project modeled what happens if a major New Madrid event takes those pieces of infrastructure offline at the same time. The answer, in short, is a national-level economic event that ripples out through supply chains for months. It is worth stopping for a moment on that word, months. When California experienced the 1989 Loma Prieta earthquake, the Bay Bridge was back in service in about a month, because California had already invested billions of dollars in the engineering, the equipment, and the trained workforce needed to repair damaged bridges quickly. The New Madrid region has not made those investments to anywhere near the same scale. If several major Mississippi River bridges go offline at once, there is no equivalent bench of resources standing by to put them back into service, and there is no easy detour for a river that wide. The difference between California preparedness and New Madrid preparedness is not luck. It is decades of investment. California has been retrofitting bridges, requiring seismic building codes, and drilling school children on earthquake safety since the 1970s. Most of the New Madrid region has not. Older homes in Memphis are often wood frame houses built before 1980, not bolted to their foundations, which means that during strong shaking they can slide off. Mobile homes, common across parts of Arkansas and Missouri, sit on cinder blocks that can shift during an earthquake and rupture the utilities connected to them. Schools built before 1970, some of them still URM construction, are packed with children during the daytime. Hospitals in smaller cities were built without lateral force resistance in mind. This is not a criticism of the people who live there. It is a description of a region that has, for 100 years, been given very little reason to think about earthquakes. But here's the problem that USGS scientists keep coming back to. The absence of memory is not the absence of risk. Now let us talk about what USGS and CERI, the Center for Earthquake Research and Information at the University of Memphis, are actually watching for. Because the alarms are not being pulled at random. The first signal is the ongoing low-level seismicity. The New Madrid zone produces roughly 200 small earthquakes per year, most of them below magnitude 2. Occasional magnitude 3 to 4 events are felt locally. That background rate is monitored continuously, and any significant change in the pattern, any cluster of moderate quakes, any migration of activity along the fault, or any deepening or shallowing of hypocenters is watched closely. In geology, a small change in a long stable pattern can be as important as a single large event. The second signal is paleoseismic evidence, meaning the physical fingerprints of past earthquakes preserved in the ground. Since the 1980s, USGS researchers have carbon-dated sand blows and other liquefaction features across the region, some of them going back thousands of years. That work has revealed a recurrence pattern for major New Madrid earthquakes on the order of roughly 300 to 600 years between big events. Since the last full sequence was in 1811 and 1812, we are, in the words of many researchers, in the early to middle portion of the current cycle. That does not mean the next big one is imminent, but it also does not mean it is far away. The uncertainty on that number is very large. The third signal is the assessment maintained by the USGS itself. Based on decades of geologic research and expert workshops, the current numbers are approximately a 7 to 10% chance of a repeat of the 1811 to 1812 sequence in the next 50 years, and a 25 to 40% chance of a magnitude 6 or larger earthquake in the same window. To put 25 to 40% in context, that is comparable to the odds of a coin coming up heads 2 or 3 times in a row. It is not an emergency alarm, but it is not a rounding error either. The fourth signal is the ongoing scientific debate about GPS measurements across the seismic zone. Some studies over the last decade or so have found little to no measurable ground strain accumulating at the surface. That led to headlines suggesting the fault was shutting down. USGS convened a formal expert workshop in 2006, and again in later years, to evaluate exactly that claim. The expert consensus was that the GPS data alone was not a convincing reason to lower the hazard assessment, especially given the paleoseismic record and the ongoing low-level seismicity. The physics of stress accumulation in deep failed rifts is not yet well enough understood to say confidently that a lack of surface strain means the fault is safe. Scientists generally do not conclude that it is. To put that debate in the plainest possible terms, the surface of the Mississippi Valley is not measurably moving in the way that the surface of California is measurably moving. But the deep crust several kilometers below the surface may still be quietly loading stress on old fault segments that only release every few centuries. Missing surface strain in an intraplet setting is not the same thing as a safe fault. That distinction is exactly why the USGS has kept the New Madrid hazard assessment on the National Seismic Hazard Map, which in turn drives the model building codes that most of the country uses today. Keep an eye on building code adoption, too. The states inside the seismic zone are slowly moving towards stronger requirements for new construction. But most of the buildings the 11 to 15 million residents actually live and work in today were built long before those codes existed. Retrofitting is expensive. Public awareness is low. And that mismatch between where the risk actually lives and where the money is going to be spent is exactly the gap that USGS keeps trying to close. To put all of these signals together, the most realistic worst case for the New Madrid seismic zone is not the fault suddenly failing tomorrow along its entire length. That is not how faults like this typically break, and scientists generally do not conclude that it will. The realistic worst case is a magnitude 6 or high 6 earthquake, close to a major population center like Memphis, on a fault segment that has been quietly loading stress for 2 centuries. That is the event the USGS considers most likely inside a 50-year window. It would not destroy 8 states. But it could devastate one city, kill hundreds to thousands of people, and cost tens of billions of dollars because the buildings were never built to survive it. If that combination lines up in any given year, the response window for prevention was decades ago, not weeks from now. So, let us bring this back to what you actually need to know. The New Madrid seismic zone is not about to break tomorrow. Despite dramatic online headlines, there is currently no scientific evidence that a repeat of the 1812 sequence is imminent, and there is no reliable way, anywhere in the world, to predict the exact day or year an earthquake will strike. That is not what serious USGS scientists studying this system are saying, and it is not what the monitoring data shows. The idea that the fault is decades overdue is not supported by the recurrence interval math, and neither is the opposite idea that the fault has shut down. But the most realistic danger is not in a distant history book, and it is not on the other coast either. It is what happens if a moderate to strong earthquake, in the 25 to 40% probability range, strikes a region where most of the buildings are unreinforced masonry. Most of the homes are not bolted to their foundations. Most of the schools were built before seismic codes existed, and most of the residents have no earthquake insurance. That combination could turn a magnitude 6.5 or 7, which would be a serious but survivable event in California, into a catastrophe in the American heartland. That is the real threat. Not an apocalypse, a mismatch, a modern, unreinforced city sitting on top of an ancient, failed rift that everyone forgot about. So, before you go, if this breakdown made the situation clearer for you, hit that thumbs up. We are trying to get to 5,000 likes on this one, so YouTube actually shows it to the people who need to see it. And drop that comment. Tell me where you were the first time you ever felt the ground move. I read them all. Let us go. See you in the next one.